All right. I think the thing says we're live. Let's try. All right. I heard that clap. Now, I'm not sure how NVIDIA is adjusting my audio drivers. It's probably focusing my volume down because I am quite loud. Even when I was on Kurt's channel there, when they were doing the little theories of everything thing, I totally gave feedback. It was very noticeable. We all have different rhythms, different. My voice is grating. I understand that. At least according to Twitter earlier, knowing is half the battle. All right, all right. So, where are we at as we begin our broadcast across this internet of stuff and things? We're going to let some folks roll in. Why? New Year's Eve. At least it still is on the East Coast. Happy New Year, Denmark, and all the other places in the future. Okay, I think including the UK now is at GMAT -5. All right. It's 900 hours, something like that, a little past. All right. I think that's how that works. Oh, who would have thought time dilation and relative stuff involving time might confuse people's brains? I still don't get it. But daylight savings time jokes aside, for now. But all right. The title of the stream and the totally recycled thumbnail from a whole bunch of stuff in the past. We have, I can't necessarily say this is a vacuum energy explanation part two, because I don't really have much. Okay, maybe we have some more stuff. Maybe there's a few more calculations. I realize I'm not the biggest fan about going back. I still often go back and do the same things. Why? Because there's always new folks and everything. But it's like, unless I really have something new to share, it's like, uh, that's one of the things I get obsessed with is searching for stuff because it's number one, I'm not a physicist, I'm not a mathematician, I'm a gamer. Yes, I'm showing three fingers because Sonic 3 was supposedly amazing. I still haven't seen it. I've heard good things. I've heard good things. But we're gonna have to maybe we'll do a physics of Sonic because I still have there's a paper on the Death Star and the amount of energy it takes to literally obliterate Alderaan and like the surrounding circumstance. They actually went in really deep. I was quite impressed. I should probably actually go through and actually replicate more than maybe one. I don't even think I went through any of them. But hey, WWKK, Happy New Year, my friend. Good to see you here. So, all right. So we just have our standard stuff from the other day. So since I now have an eraser and I'm attempting to get combobulated, oh, it actually works pretty well. All right. First stuff being erased actually works pretty well. Okay. Well, gonna spend like $60 at Staples. I'm sure I could have gotten it for a far better price and a far larger board from Temu or something like that. And listen, hey, if something makes you happy, I bought a TV that I'm still typically using if I need to from what's it, overstock.com or whatever it was at the time. And I mean it still works. The box it came in was pretty beat up, but hey, it worked and it was cheaper than buying a new TV at the time. Now it's, I don't know, $500 you get what, a 55-inch freaking 60. I don't even know. See, like 80-inch wall mount TVs, they're flat and like a lot of these things are actually really light. That's the impressive thing. I still remember having to move around like some of the old friends, like where they were on top of like the new like plasma TVs and HD and everything. Because they wanted to watch the footballs and stuff, moving those dudes around. Freaking like a piece larger, heavier than a piece of furniture. It's like, all right, we're moving this thing because well, that's not the plasma thing, so it's like 200 something pounds and it's bulky, and you don't want to like get into a part that like breaks, and then you break a freaking like wicked expensive TV. That would be terrible. Okay, I'm allowed to say wicked again on a more constant and frequent basis. Why? Because at least I'm on the East Coast now. It's good to be back. You can definitely tell it's like, all right, there's a lot more moisture in the air. My skin, my skin thanks you, number one. Oh, did I already break it? Sorry. But yeah, and about 4,000 feet lower sea level. That's an interesting thing. I think it's noticeable. I don't know. Haven't been back long enough yet. All right. I did usually notice after Florida. You spend the week down in Florida, it's like, all right, I'm just starting to get used to the temperature. And then you come back and you're like, oh my God, it's so cold. Why is it so cold? And I feel like, I don't know. I think it kind of depends on how you grew up. But what are we doing right now? Okay, so the whole vacuum energy catastrophe, let's do this. All right, we'll go into over here. This is this dude. All right, so share with the class. The cosmological. This is the best thing that I can find to explain it. And of course, I'm not here to. Okay, I'm full disclosure. I'm here to cause problems. I just want people to think. If you're going to use the moniker, the means of destruction, yes, the means of production may have been taken in all its relevant forms, but sometimes before creation, there must be destruction. All right. So yes, Wikipedia needs more money. I'm okay with donating to Wikipedia. Why? Because I use it. I have a I have a hankering that if I was in the public limelight more and express some strong political opinions, my opinion of Wikipedia might be a little different. But that is not the case, my friends. So let us science. All right. So the whole thing, the cosmological can from our friends at Wikipedia, the generalized thing that will AI generate if you look for it. Cosmology, the cosmological constant problem, or vacuum catastrophe, is a substantial disagreement between the observed values of vacuum energy density, the small value of the cosmological constant, the much larger theoretical value of zero point energy suggested by quantum field theory. So, coincidentally, here's a random piece of deep lore for some folks. May want to look into it. It's probably nothing, but the whole, I guess, concept of vacuum energy and zero point energy may have helped come from a 1981 paper that Stephen Wolfram did with Jam Amjorn about the thermodynamics of the vacuum. And a couple of years later, Robert Ford, another physicist slash sci-fi author, is like, "Are you sure your calculations are correct?" He's like, "Yes, I'm pretty sure my calculations are correct." He's like, "Well, if your calculations are correct, there exists somewhere something doing basically a Carnot cycle, basically a perpetual motion style thing." Now, to sum up a whole bunch of words that that you randomly hear Stephen Wolfram say on a live stream, he does like these things like twice a week, like about Q&As and different stuff like that. But he just shares these random stories because he was in the business, so to speak, of particle physics, and he's like, I look at what he said and he's right. I'm like, wait. You just so casually say that what this other physicist and sci-fi author said was right. That, that there may be a way to quote unquote extract energy from the vacuum. Now, he said basically you probably couldn't do it with matter because you wouldn't be able to shield all the wavelengths, but he suspected it would be possible with some form of a field configuration. I say that because I'm also very biased, and that sounds like something that maybe suggested by some of the things that Thad has proposed. So, say, hey, happy New Year, Nuno. Good to see you, my friend. Good to see you. Yes, we're going to. Okay, so what the heck is the vacuum catastrophe? We should probably actually continue rather than me just rambling about random things. Okay. Depending on the Planck energy cutoff and other factions, the quantum vacuum energy contribution to the effective cosmological constants calculated to be between 50, as many as 120 orders of magnitude greater than has actually been observed. The state of affairs described by physicists as the largest discrepancy between theory and experiments in all of science. Now, some people say that. I believe Dr. Hossenfelder would say that's not the case. Uh, because it's like, what did they actually say? Okay. So Okay, let's just randomly go again. I am not a quantum mechanic. I'm gonna do it on the internet. But let's look at something slightly different. Okay. Let's go. Do Wolfram Alpha. Okay. So how about this? 120 orders of magnitude. Okay. So what's the vacuum energy density? Let's just go to Wolfram Alpha because it's magic because you type if I spell vacuum right. Vacuum. Hold on. And we need to do universe is where otherwise we need to specify vacuum energy density. Okay. So basically rho lambda. God, I called it P lambda for excuse me, P vac. Rho vac. So rho lambda about 5 times 10 to the negative 10 joules per cubic meter. Okay. Energy density. Okay. So we got rho vac there. All right. So if we have that, and that's the observed vacuum energy density. What's the problem? Well, let's take that, divide it by the Planck pressure. Just, just a hunch. Oh, look. Let's do that the other way. Do one over the other thingy. 123 orders of magnitude on a small scale. Oh, look. Plus 123. That's about 122 orders of magnitude. WTF, mate. So basically, long story short, I think the issue, and again, I'm not a licensed quantum mechanic, is that we're calculating things should be at the Planck pressures. It's about 113, 10 to the 113 pascals or whatever. It is the pascals for Pascal because we're doing this and it's like 5 times 10 to the negative 10 rather than 10 to 113. So that's about 122 magnitudes off. Okay. So what if, and okay. So when we're doing these, basically this is the Planck density times c squared. This is the energy of the Planck density c squared. Why? Because now we're taking the energy and then we're doing our c squared. We're taking our mass, we're doing the c squared equivalent thing. So then we get the really large number. Okay. Wait, now we go to the Planck pressure. Okay. So we're like, yeah. There's our energy magnitude difference. 8.7 times 10 to the 122 orders of magnitude. All right. How do we reconcile this? People have a lot of ideas. There's a lot of really smart folks out there. Now, the best solution I found is I listen, I don't think we should beat dead animals, but my thought is here there are some points that might be worth repeating. What the heck am I talking about here? Okay. So certain things that we learn. Number one, yes, I'm gonna go through this whole dang thingy again. And do the find structure constant. Okay. We get alpha. This number here, it's got no dimensions. Okay. It's my mouse slowly gets bigger from lag. All right, definition. E, which is elementary charge. That's squared. And then we divide that by 4 pi. That's the speed of light c times the electric constant epsilon naught times the elementary unit of action h bar. So that interpretation is the electromagnetic coupling, my friends. Okay. So you get this number here. And you look at this and you're like, whoa, this is a dimensionless number. How can it be dimensionless? Let's try to dimensionalize this, my friends. That's the first term. The first term is elementary charge. So we got a charge thing. Let's square it. Okay. If we square it, that means we have a charge squared term. Ah, a clue, my friends. So wait, if it's dimensionless, that means we got to have a charge squared divided by a charge squared. Now, again, I'm not a logician, but I think that adds up. Okay. Does that mean this is charge squared? What charge squared might it be, my friends? Well, if we take this and we make an assumption, how about we do this? Let's do our magic on Wolfram Alpha. Elementary charge. We're gonna computationally reduce it. This is just a hunch. Use the Planck. I can spell charge. All right. And we square it because that's what we do in physics. Oh, look. Number looks a little familiar. Looks an awful lot like that. Wait a second. This is the fine structure constant thingy. Wait a second. 0.007. 0.007. 297. 297. 352. 352. 56. 56. My friends, according to Wolfram Alpha, that is the fine structure constant. Now, I might disagree with that last digit there. There may be something interesting going on. Then again, I just could be wrong. So I'm just injecting some opinion there. Hey, Kevin. Monty Python. I love Monty Python. That's what. See, I say a lot of things, and I have to apologize for a lot of things because I crossed the line. The general line that I keep in mind is Monty Python. It's been on Monty Python, and you've displayed it, and you're attempting to do it in an excellent way as I scare everybody away. Oh, God, he's going to Monty Python mode. But Happy New Year, my friend. Yes. May our numbers be large and our large numbers be. I think it depends on the perspective. We might have finite stuff within our realm, and I have to say realm because we're gonna get conjecture, it's finite. Universe, big U, it's everything. So a mind like mine goes, what be out there? I don't know. The RB Dragons, I don't know. Let's go back to our little thing. All right, so what are we doing here? Little fine structure constant, we were able to computationally reduce from this thing, which is a very beautiful, so you get an elementary charge squared. So like, all right, you got a charge doing this thing. All right, you got this thing going. Oh, we're squaring it. We're trying to like get it to come back around, set up in an orthogonal type of way, times a spherical thing at the speed of light via the electric permeativity of free space by the elementary unit of action. I mean, that sounds about right. And we get this number. We can also get this number by taking elementary charge squared divided by the Planck charge, and we square the whole dang thing. It's shorter to literally type in. At least for me, I don't know how to do all the fancy symbols that fast. Pardon. All right. So where are we at? So here's where we're at. I have a marker thingy somewhere. There it is. All right. So we're gonna start over here again. We're gonna do our alpha fish equal to elementary charge over the Planck charge. Okay, we square that. All right. So number one, notice the thing, and of course, the lamp is. And okay, let's move it down. This is here. That's the simplest thing to do for people to actually see, right? Oh no! Start thinking in the other direction. This one. All right. We got our alpha fish. Is that equal to elementary charge over the Planck charge? Square it. Okay. It makes me feel so much better. All right. So now at least people can see that. All right. So that's number one. We go back over here. Yes, I'm laying out the case. Don't worry. We're going to get to a point here. I This is just the best way I can actually explain it, is actually just doing it. And it's the wonderful thing is it's like you know, go in there and type the word. That was what allowed me to do it. That was the power of the Wolfram language. It's like if I had to look up all these things in code and have an entire tab of code, you can do that. uh, But if you can literally just type it in, and at least you're getting about five, usually 5 digits of accuracy for a lot of things, then that's pretty good, at least in my opinion. Okay, what am I doing? Alpha. Okay, so the other little thing that we noticed is, all right, we do that. It's like, this isn't exactly the vacuum catastrophe. Ultimately, these things are all going to be related somehow. Now, can I say, I'm not saying that directly. We're just following a schema. We're taking stuff, we're dividing it by a thing, and then we're squaring that whole lot. Why? Because we can. Okay. So when we do this, so like the Higgs boson mass, let's just take the Higgs mass. Easier. Higgs mass, let's divide by the Planck mass. And let's square the whole darn thing. So what do we get? We only really know the Higgs mass to about 3 significant digits. But it's about 125 in giga-electron volts. It's like 2.23 times 10 to the minus 25 kilograms, something like that. I've spent some time working with it. The paper is almost done. Okay, so our result is we get 1.05 times 10 to the minus 34. Okay. Now, for most folks, that shouldn't mean a dang thing to anybody. It's like, oh, that's a really small number, right? Yeah, it is a really small number. Coincidentally, if you take the, if you divide that magnitude into the elementary unit of action, you get about 1 joule second. WTF, mate? Uh, wait. Why is that 1 joule second? Well, what is H bar? H bar, Planck's reduced constant. The elementary unit of action. Wait a second. Aren't we just working with the elementary unit of charge, basically the magnitude of charge of an electron or a proton? Elementary charge divided by a Planck unit squared equals alpha. Find structure constant. Now, wait a second. What is H bar? H bar is H, our Planck's constant, divided by 2 pi, because there's a 2 pi factor difference there. 1.05 times 5, excuse me, 1.055, it's actually 4, because the next number is like an 8 or something. So 1.05 times 10 to the minus 34 joule seconds. Right, 1.05 times 10 to the minus 34. That that sounds a little familiar. Why does it sound familiar? Oh, hold on. Need to duplicate this because we need to go back. Okay. So let's go back. Why was that familiar? Wait a second. 1.05 times 10 to the minus 34. 1.05 times 10 to the minus 34. Oh, let's do more digits. Okay. Yes. Okay. So 1.05, some more digits, times 10 to the minus 34. 1.05 times 10 to the minus 34. That's interesting. I will finish the paper this upcoming year. Sooner rather than later. Okay. It's the Planck boson and Joule conjecture, or educated guess on the mass of the Higgs. Uh, because what are we doing? Let's go back. We got 1 joule seconds. Why? What if we assume that this squared relationship, dimensionless, was supposed to be equal to that? Because we had alpha equal to that. What if? Well, we need to get the dimension out. What's h bar? Bar is uh, this is how we do it. We find what it is. H bar, joule seconds, angular momentum. All right. So okay, action. So joule seconds is the dimension that we use. All right. So well, let's set it equal to its one. The one is joule seconds. We turn into a dimensionless number. Do this. Okay. So we'll get the elementary unit of action divided by its dimensions of action. It's equivalent 1.05 times 10 to the minus 34. Yes, there's another 5 there. Technically, it's a 4, and then it's 7, 8, whatever it is. Um, but okay. So if we were to assume that that was supposed to be equal to this magnitude, what if we did our equal sign? And since we've measured the Higgs mass to about 3 significant digits, the Planck mass we've calculated to 5, 7 with error, and h bar is defined at 10. So if we only know this will guide to 3, what if we do a little magic and we ask Wolfram alpha, let's solve for x kilograms. Okay, go Wolfram alpha. This means we have the elementary unit of action divided by its dimensions of action to get a magnitude. We're setting it equal to a mass that we're solving for, divided by another mass. Those cancel out. And this is squared relationship. Okay. And the dimensions cancel out. So we got a dimensionless number equal to the magnitude of the elementary unit of action to solve for a claimed conjectured mass of the Higgs. Okay. Number is also interesting. Okay, and again, it's a squared. We get a positive and negative answer. Okay. So this we were solving for kilograms. So we can add our dimensions safely back in. Oh, about 125 GeV. Seems to be pretty close to the mass of the Higgs boson. What a nifty little thing. I mean, again, we're gonna need higher precision and stuff like that because it's only 3 significant digits. And our confidence in the Higgs will home in. We'll get a little bit more precise. So if we happen to do c squared, because a lot of times I like to talk about it in GeV. Let's talk about it in GeV. So we do that. Okay, so we get it in these Newton meters. How delicious. Okay. Okay, in GeV, it's 125.37 GeV. Okay. So it's about the mass of the Higgs times c squared. Okay, that's what you already said before. Okay, so let's get a little additional information. What is mass of Higgs boson? Okay, so 125 GeV, blah, blah, blah. According to CMS, most recently is 125.35, 24.37. All right, okay, that's pretty good. The precision of 15. Okay, so that's in 1 sigma. This Atlas most recent is 125 GeV, 125.11. I can see a 0.9, so that's about 2.5 sigma in there. Okay. And then and apparently it's important for reasons. Okay. So for yes, see that's one of the things. since I don't have a historic background, listen, I haven't taken physics 1 through 3. I haven't taken thermodynamics, electromagnetism. I haven't taken all that jazz. I did take a modern physics class for about a week and a half my senior year because it seemed like a cool thing. And this is early days of the system, which still lets you abuse it and everything. I was able to start doing some of the homework and everything, but apparently lattices confused me. But maybe they're not as confusing as we were confused about. But yes, 1 over, I believe it's the square root of mu naught times epsilon naught gives us the speed of light. Uh, yeah, see, that's the thing. That's the thing. That's probably not a bad thing. 6 sigma, it's like 5 sigma. Okay, that's pretty good. It's like 6 sigma. You need some real good precision. How we do that? Looking for group muon collider. That's probably realistically what it's going to take. So if people really want to do it, maybe we'll see it in 10 years. Uh, who knows? They were able to get muons up to about 8% the speed of light, and then you need to collide them so you're getting into straight. Humans are amazing at what they can do. That's the thing. Don't doubt what we can do. Sonic, or he can do it. Sonic the Hedgehog, something like that. Okay. So what's the whole point? The whole point is we're trying to simplify this, so we'll continue. So we have our alpha side equal to elementary charge divided by Planck charge squared. Okay. So let's make this claim. We'll do h bar do its magnitude because it's prettier. That's all we really did. We just divided by its unit. Is equal to mass of the Higgs, m sub h, divided by the Planck mass, m sub p, and we square the thing. So wait a second, wait a second. This is an elementary thing. Alpha is equal to elementary charge divided by the Planck charge squared. The magnitude of h bar is equal to the mass of the Higgs divided by the Planck mass squared. Groovy. Now again, that's a conjecture. Like this is basically okay. We've got to at least Wolfram out to like at least 9 significant digits or so. It's like we got fast. This conjecture is good for what, like 3 significant digits. It's like we're gonna need much higher precision. We're gonna try to need to probably really measure it to about 7 significant digits, and then there would probably be some energy exchange or something to go on to get to the full 14 significant digits, at least within the model we're using primarily at the monastery via VAD's 14 digits conjectures. All I know is basically if Newton gave us 7 significant digits and Einstein went along and gave us 7 more, and then co-data, we have basically 14 significant digits for our best precision measurements. Might there be a coincidence? I don't know. Okay. So since it's now been at least half the episode, let's actually get into what we're trying to talk about. Okay. I need that. Yeah. To be fair, I do think it probably does depend on the bench. Okay. When you do the calculation, okay, we'll do a real quick tangent. So basically, Thad basically just gave you some conjectures. He's like, well, it should be something like this. We have Planckian boundaries. If we're going to say there's going to be some hyperbolic figure eight knot articulation giving rise to its complement, which does project a toroidal boundary, somehow we're going to invert that thing, and you're going to have things like the Planck length be expressed in their inverses. So what do? Well, you do meter squared over Planck length. And then you get to draw out a really large number. Groovy. All right. What am I showing here? Oh, the whole point is, let's go to this guy. Dimension 4 hypersphere with radius that we were just talking about. Okay. Okay. So this gives you a 4-dimensional hypersphere. This should be a sphere in 4-dimensional space. Okay. All right, so you get this giant thing. So the content 7.2 times 10 to the 139 meters to the fourth. Whoa. I am in the fourth dimension. Wow, it's okay. The hypersurface area. So the three-dimensional surface on that hypersphere is expressed in cubic meters. I can kind of try to wrap my head around that. Uh, it's 4.6 times 10 to the 105 cubic meters. Okay. The interesting thing is these are like the same numbers because just when you go up in the dimension, the calculation, that these end up being the root numbers basically based upon your radius input there. Uh, I think it's like 2 pi squared or something is like the factor between these. And that's why it's like, like, why are these numbers different? And then you realize like it holds for as you go up in the dimensions. You're like, oh, uh, so it's a higher dimensional double cover? I don't know. But okay, so I was just showing that for a second. Now, why have I shown these other things? Okay. I don't need that. And all right. So let's get back to what we were actually doing, the whole reason why I was setting that up, so we can take a look at another way. Now, Thad has recently also put out a video about Gauss's arithmetic mean, or maybe it was the geometric mean, but he was basically talking about what happens if you have different stuff coming together and you were to take the roots and how those seem to connect. There's some very interesting geometry um, that may explain a lot. Okay, we'll leave it at that. It's Thad Roberts. If you would like to check that out, should be in. If you go to my little thingy, should be in a recommended channel. Okay. Okay. So basically, we have all these things. Okay. So where is it? Let's go to. Let's make it bigger. There we go. All right. Big one. All right. So estimate that. So these are based on the measurement. So the Planck satellite basically does 3-year mission. So that's why you'll see like Planck 2015, 2018. The mission was from 2015. Um, Measurements by the Planck collaboration. So these give you estimated values. So you've got rho vac here. So basically the conjecture energy density of the vacuum, and it's expressed in kilograms divided by meters cubed. Okay, so basically it's going to be a meters cubed term unless you're going to geometricize the GeV. Well, it's kind of fun to say. Geometricize the GeV. I'm sorry, I'm very easily entertained. Or about 3.35 giga electron volts per meter cubed. Okay. So the reason why I say it might be useful to uh, watch that video, which I still need to do myself. I know I was there. He explained it to me. I just I think it might explain a lot. And why might it explain a lot is okay. Now let's extend our conjecture. Let's how the heck do we get these numbers? All right. The full disclosure, I was trying to verify. Let me get rid of that guy. The full disclosure, I I wasn't trying to figure out something for this. I looked at this. This is very pretty. And it happened to come out to be 1 joule second because I'd written it the other way that uh basically was I think I inverted it. So I did what is it MP, so the Planck mass over M sub H, mass of the Higgs. I squared the whole thing, and rather than dividing by H bar, put H bar over here. But if I'm going to solve for X here, when I was solving for X, I had to set it equal to something because I'm trying to solve for this amount. So I was solving for X kilograms. So I just set this equal to what Wolfram Alpha first told me was 1 joule second. That's the dimensional unit of action. I don't make up the rules. I don't know, guys. The universe does, or at least how we frame it is something consensus science. Uh, yeah. So I had originally written it like this, and I just said equal to 1. Doing this, and then just doing h bar divided by 1 joule second. You just do that, and you get this handy dandy little graph. So it's where is it? No, no, it was another guy. That was. Oh, sorry. Where is that? Oh, let's just go to the thingy that we had. Oh yeah, this guy over here. Yeah, yeah. See, it gives you the positive and the negative one, so gives you more information. And then I think we need to invoke our positive mass conjecture or whatever that is, and it seems to all work out happily ever after. But well, to be fair, yeah. I mean, if it is a scale, the thing is, I think it's at least in my opinion, I just could be wrong here, but it's like I hear people say it's like, oh, we need to solve it. And again, I'm not smart enough to actually know the problems. It's just I hear folks say it's like, well, why is this set equal to that? So it's like, well, I don't have the answer, but I'm like, oh, what if the magnitude of the Higgs boson's mass had to be the magnitude of the Higgs boson's mass because its squared relationship allows for the elementary unit of action to take the magnitude that it does to act. I mean, that's a crazy bold claim. I don't even know. Maybe that's just a dumb thing to say. Uh, but that's just how, from my perspective, as like if I'm a gamer or trying to put together a puzzle or something like that, well, if that happens, and again, it's going to depend on what the measurements are, and it probably will go off. Maybe it'll have to be divided by a factor, but it's for 3 digits and at least the corresponding magnitude. So just look to see what might happen. So all right, erase this guy, and where are we going to go? All right. So the whole point of that is just like that concept. And we just do this. Okay. So what if we were to write it something like this? Now, 1 joule is interesting. Here's is the interesting thing because if you take c squared and you take its energy or its mass equivalent, the amount of that conversion, basically the relativistic mass of 1 joule. And that's it. We have to take a look just because it's such a fantastical thing. I know we got to nerd out. We got to nerd out in the new year. So c squared. We still get the speed of light squared. Okay, we gotta say it's a unit because it wants to think it's a variable. We get this number here. Pencil 16. Oh, that's pretty cool. All right. Well, as we've learned from some of our friends, let's invert it. What might happen when you go back to its unit? We get this very interesting number here. 1.113 times 10 to the minus 17. Second squared per meter. Kilograms per joule. Joule, you say? Wait a second. Kilograms per joule. Mass per energy. The mass energy conversion of c squared. Groovy. So what if let's legitimately just do 1 joule second. Oh, wait. 1 joule. Sorry, I'm going back to the other thing. Oh, it conveniently gives us that number 1.113 times 10 to the minus 17 kilograms. Okay, the relativistic mass of 1 joule. Okay. So what if we take this number here? What if we assume the speed of light was telling us something? Let's set it equal to something. What are we going to set it equal to? Well, listen, this is totally crazy. I'm just saying we're taking the square root of the Planck mass because that's, I've been using the Planck things, and I was trying to solve for some kilograms. Well, why not? So let's do the Planck mass. Multiply it. Well, I don't know what I'm looking for. So it's like, all right, let's multiply it by X kilograms. What's we got to do? Let's uh, vacuum energy. All right, if we conjecture it's going to be some form of a hypersphere, why? Because I already leaked the beams and showed some hypersphere calculations. All right, so we need something spherical. How about divided by pi? Um, but it's not just pi because we got to figure out for 3 dimensions. Ah, yes, 3 divided by 3. And we'll close that. Then we're going to hit enter. Now, I understand I'm a crazy person on the internet. Every once in a while, I made a horrible fatal error. Whatever shall I do? What did I do? It's cool. Give us a mass. That should give us a mass. That should. What have I totally done wrong? Oh, derp. That kilo. Hold on. Oh, we broke the science. We broke the science. Did I? Let's make sure this is. Okay, it's giving us a kilogram answer. All right, let's bracket it. Because it made me nervous. Oh, doing it as a variable, is that what happened? I don't know. Like mass. Trying to solve for x. I haven't done this in a while, but do I need to? Oh, I express it like this. Well, 1/2 root is about like that for some reason. Yeah, that was. Yeah, that was it. Like if you try to take the square root of -1, it gets a little wacky sometimes. You need to raise it to the 1/2. They're doing the same thing, but you're going about it a slightly different way. Since it does that, it convenient gives us 4 answers. Why? I don't know. Is it a 4-dimensional hypersphere? Oh my god. So we're solving for kilograms. All right. So what's this number here? We got 5.9566 times 10 to the minus 27. What was the thing you were looking for? 5.96 times 10 to the minus 27. All right, so 5.96 times 10 to the minus 27 kilograms divided by meters. 5.95. All right, if you're round up, maybe that's a 6. All right. Times 10 to the minus 27. Okay, and we're solving for kilograms. Let's put the kilograms in there, but there's no meters cubed. What are you doing? Okay, so we're getting these things, but how do we justify meters cubed? Okay, I just take this and divide it by meters cubed. No, you don't just randomly do that. That's not what we put in. That happens to come out to be approximately the universe dark energy mass density, but I digress. The usual big reasons, potentially. Okay, so, but what did I do? All right, means we want it in meters cubed. Okay, divided by meters cubed on that side, divided by meters cubed on that side. Oh, it appears to be the same number. but now we can write it in 5.956 times 10 to the minus 27 kilograms divided by meters cubed. Hey Tommy, happy New Year, my friend. Yeah, we're just pawing along ourselves. Just all right. So long story short, what voodoo have you done here? All right. The only claim is all right. The speed of light. God, how far did I go? Have I gone far enough? Let's go farther back. All right. Okay, so we're gonna do this. We're gonna treat it like going Super Saiyan. How do we do this? All right. You let's look at we don't wanna I'm not gonna you've heard us say the speed of light. Well, how about c squared? As a unit. It's this almost 9 times 10 to the 16 meters per second. Because it's speed squared. What happens if we do 1 over c? 1 over c, the inverse of the speed of light. You get this convenient number. 1 times 10 to the negative 17 kilograms per joule, aka the relativistic mass of 1 joule. That it says right there. Okay. Oh, so basically, if you take 1 joule and you divide it by the speed of light squared, you get about 1 times 10 to the minus 17 kilograms. Okay, what else? We move on. We need to. Uh, okay, so we go back here. Joule over the speed of light squared, 1 times 10 to the minus 17 kilograms. All right. We set that equal to the geometric mean of, all right. So we take 1. We're going to take the speed of light squared, and we're going to divide out the mass equivalent of the unit of 1 energy, 1 joule. We get a mass term. We set that equal to the geometric mean. So basically, we take these two math, the Planck math, boundary of mass within our 5 dimensions of measure: time, space, charge, mass, and temperature. Those flavors, we can get all the rest of the stuff and things I play. All right. So we take the Planck mass, we want to solve for x because we think the speed of light is an important thing for some reason. And we multiply that together, but within this geometric root, because we're just taking the square root of these two things, we get two masses together. That give us mass squared. That's a wonky term, so that's where we need to get the root out, so we can get 1 dimension of mass. Oh, within this whole thing, we divide by pi, and we divide that by 3. Coincidentally, the number of dimensions within meters cubed, which if we actually do it out, we just add in the meters cubed on both sides. The dimensions that we're talking about. Oh, we got this 5.9, 5-ish. Oh, rho vac, eventual mass energy of the vacuum, 5.96 times 10 to the minus 27 kilograms per meters cubed. Oh, look. 5.9566 times 10 to the minus 27 kilograms per cubic meter. Approximate the universe. Dark energy mass density. It's just, I'm just about the vacuum energy density. I'm just saying it's probably coinky dink. Let's say we want to, okay, we don't want its mass equivalent. Let's forget about our mass. Let's just do it by a joule. Joule is an energy, of course, of course. All right. So we take our joule, and now we're going to do energy. So we go from mass to energy. Because you can just write the words. And let's solve this. We're sitting equal to 1 joule. Let's say equal to joules. So we're going to solve for x joules because we can. It sounds a little dirty, but it's not. Okay, we're doing the same thing. Oh, okay, lucky. It gives us. Oh, well, that's fun. All right, so we got 5.354 times 10 to the minus 10. What are we looking for? We're looking in joules. 5.35, excuse me. 5.3566 times 10 to the minus 10. Uh, This 5.354, 5.35 6. Okay. Okay, like the first three digits times 10 joules divided by meters cubed. Okay. So let's how about this? Let's do GeV. See what it is in GeV. Because this is where it is. So we get 3.341 GeV. What are we looking for? 3.35 GeV divided by meters cubed. Oh, I mean that seems to be at least the first like two-ish, three significant digits. I mean that's kind of neat. Uh, they've Listen, that's the thing. I think there's a lot of positive stuff and things coming. I claim. God knows we need it. Hey, upcycle. Good to see you, my friend. Good to see you. Now we're just trying to see if we can maybe solve a couple of vacuum catastrophes. It's or at least conjecture. This is technically the PB&J conjecture. Shouldn't that be for the Higgs? Is this dark energy a boson? Is this just a thing that's happening? Why? It's like I'm just saying. If you take the Planck energy density and then you square it, then you get that. And to be fair, I didn't really get much further. Actually, so I could do some calculations and get some fantastic numbers that I would claim maybe are telling us something. Exactly what it's telling us. I mean, that's what I need you all's help for. So let's what were we doing here? All right, let's finish filling out this little board thingy because we can. All right. So what if we just did something like this? It's like, all right. So we got the speed of light. So we did the, oh, is it 1 over the squared is equal to, is it the magnitude of a joule divided by c squared? So 1 joule over c squared. So no, magnitude. Use your eraser, you savage. There we go. That's why we got it. All right. So we have that there. All right, that's cool. So, well, what do we? I did the same mistake again. Oh, I'm so bad. All right. All right. So let's take something like this again, since we're actually getting the dimensions out, and actually this has dimensional residue there because that gives a kilogram. Because it's mass times c squared, which is length divided by time, each of them squared. Pardon. Let me water myself. See, the whole part about the ultraviolet catastrophe and the way we are apparently able to avoid that was this right here, like H bar. Because Planck's like, wait a second, if I can quantify this, and in order to quantify it, he was able to compute, I think, the first 4 digits or something from the data we had at the time to be like, why do I need to use this really small number? I don't know if this relates to the Higgs at all. I don't know. We conjecture maybe something's going on. Um, but for the vacuum catastrophe, uh, yeah, basically we just take this, so it's like, all right, let's just do uh, 1 joule over c squared. Protected brackets on because it makes me feel better. Okay, we set this equal to square root of, oh god, this is a good marker. It's gonna be a great year. I claim. All right, let me take the M sub p, the Planck mass. Then we're going to set it equal to, we multiply it by x kilograms, and we divide that by pi, divide by 3. Okay. And the claim is that this will give you rho. God, that was terrible. Hold on. It's silly-ish p. All right, so that should give us rho back. Actually, no, we're going to do energy. Well, to be fair, all you do is just meters cubed. Let's make people happy. Meters cubed. There we go. Now that should be, I would claim that statement should hold. And again, it's most likely wrong because most things are wrong and everything. But the reason we're writing this out is because maybe we need a little hope and maybe a little joy or something like that. People lose their minds about all this different stuff and things. Why is that? Yeah, because we're coming together. It's like we're getting more mature-ish internet culture, and people came in at different times, and people met different folks under particular circumstances. So there's all these different stuff and things, and the growing pains, of course. And legislation always lags behind for years, and then people built their lives doing particular things. Okay. So rant aside about everything else going on within the world. Let's just look at hypothetically what might be going on and a potential way to avoid the vacuum catastrophe. All right. So we're doing this 1 over the speed of light magnitude thing. Oh, because we got a magnitude thing going on. So let's keep our magnitudes going, shall we? All right. So we've got this. All right, because this is in kilograms. Oh, let's write this out. This is actually kilograms over meters cubed. Okay. This is how we can start to keep things, because now we're talking about essentially the mass energy density, and this is the mass form of that energy density. Okay. So let's just do this. Let's just, how about like this? It's like 1 joule. Like we don't need to divide to get the energy out and get our mass. Let's just do 1 joule divided by meters cubed. Looks like a crazy Erdos symbol there. I think Professor Powell's about to beat John Erdos's H index rating. We'll have to have the Powell index. That made me happy to say. It sounded fun. All right, so what are we doing here? Joule, unit of energy. Well, we divided by C to get the mass out, so we could do the mass thing over here. So let's do a similar thing. Let's do uh, energy Planck, AP. I'm gonna solve for X. I got 1 joule over here. Let's solve for joules. All right. Let's do the same little thing over here. We got I divide by 3. Take the root of this whole thing. Oh God, I really like having like a fresh marker. So we always would forget them. And then we divide this by meters cubed. And we're gonna claim that that's equal to, which one is this? It's still the same thing. It's what are our dimensions? Okay, so this should be equal to the same thing expressed in different units. Okay, that's what we're claiming. I'm claiming this is also going to be rho vac. I think there actually is a p vac, and so this is in joules per meter cubed. Then joules over meters cubed. Okay. All right. But we've got other numbers. What are our other numbers? Other numbers We need at least GeV. And we could geometricize them, but I haven't gone that far. I don't have a great enough knowledge. I should learn more. Let's look at this GeV. How can we get that? All right. So let's do this. There we go. Oh wait, we already did it. Yeah, there we go. What did we do? Oh, we just do this right here. So let's do that. 1 joule equals the geometric mean of, or the square root of, the Planck energy, and we're solving for xGeV. That's all divided by pi, divided by 3. Okay. So a geometric curvature thing divided by, well, they're looking for an answer. This is in meters cubed, technically. So we're looking for 3 dimensions. That sounds like a good reason. It took me a while. It came up from the math. It took me far longer than it should have to try to track that dude down. So all we really did was, all right, we're doing the same thing here. We got 1 joule, so that's where a broken record. Let's do. All right, so we do 1 joule. Searching for we're doing meters cubed. Put my brackets around so I feel safe. There we go. All right. We set that equal to, again, doing the square root of Planck energy, E sub P. I should probably actually drill these in. And we're solving for X. And now we just write GeV. So we can magically do it in the conversion. Divide by pi, divide by 3. And we divide this all by meters cubed. I'm going to claim is equal to rho vac in GeV divided by meters cubed. Okay. So, I mean, that's really about all. I mean, I know I've already gone over and everything, and a lot of this is a lot of the same stuff. We're saying it from, hey, you never know who's coming in here and everything. Uh, wow, it's very interesting. People come from all over, but yeah, that's about all we got for right now. And other than that, Happy New Year to everybody, and we'll see you tomorrow with some different stuff and things. Until then, peace out, everybody. Stay safe.